Hello.
Hello.
Gurusamy sir.
Start
Shall we
ma'am.
start? Yes,
Okay,
sir.
ma'am. So, good evening to all. I deem it a great pleasure to introduce our resource person of today's session, Professor Sangaran Vishwanath, IMSc Chennai. He completed his MSc Mathematics at IIT Kanpur in the year 1999. He completed his PhD degree at UC Berkeley in the year 2004. He has more than 16 years of teaching experience. His area of specialization are Lie algebras and their representation and algebraic combinatorics. He has more number of international publications in reputed journals. I thank him for accepting our invitation to be a part of this online TEW 2020 program at our college. With these few words, I welcome him to deliver his lecture. Welcome, sir.
Thank you, Professor Guruswamy and Radha.
Okay,
Thank you,
is my audio okay? I'm audible?
Audible. Yes, sir.
Audio is okay, right?
Audible, sir.
Yes.
Okay, sure. Okay. So I'm sort of I'm going to talk about this topic of counting or combinatorics. And my plan is to mostly sort of do it by way of examples rather than describe some general principles and so on. General idea will be to first see the examples and work them out, and then see if we can deduce some general principles to solve other such problems. Just like you had in the previous lecture by Professor Raghavan, I request people to just participate actively. Please just feel free to unmute yourself and pose a question or give an answer and so on. I may not be able to keep an eye on the chat while I'm presenting, because my screen sharing will sort of be the screen on top. So please just feel free to unmute and talk. Okay, so let me begin. Counting, of course, is it's one of the most basic things that we do as mathematicians, but it's also one of the surprisingly difficult things to do, in the sense that there are a large number of rather complicated sorts of configurations which arise when one studies various parts of mathematics, and where the problem finally reduces to wanting to count a collection of elements which satisfy some properties and so on. And often, there are still very many problems for which one doesn't have an answer. It's very, very tough to actually count configurations or objects which satisfy a given set of constraints. Okay, so the idea is to see if we can evolve some general principles which will allow us to do this counting in an effective manner. Okay, and my goal during my lectures will be to sort of give you a few such techniques at least, which we can try and employ. Okay, so let's jump straight ahead to the problems or the examples. So here's the very first problem that I want to talk about. So this is problem number 1. So here's the formulation. How many 4-digit numbers are there? Let's just start with wanting to count. Okay, so a simple enough question. How many 4-digit numbers are there? So what is the answer?
Sir, with repetition, without repetition.
What do you mean by with repetition, without repetition? Just 4-digit numbers.
10 power for each place we are having.
Sir, 4 9s are there, sir.
0 to 9.
Okay, so let me sort of.
So answer is 7 to 9 0.
So there are 4 possibilities, right? 4 digits, and what is the thought? How do you want to do it?
So for first position, except 0, we can allow.
Okay, so
9
you can
ways.
allow for the first digit, all digits allow 1 through 9. Okay, there are 9 digits. Then
All of us are
In
10.
second place, 10 choices.
okay, all the others are 10 choices.
10
Allow
choices.
0 through 9, 0 through 9, 0 through 9. So totally 10 choices. So let's see how many choices there were in all. There are number of choices is so 9 here and 10 here, 10 here, 10 here. And so the total will be, how do you put these together?
Product.
Sorry, what?
Take the product.
Product. Okay, fine. So you just take 9 into 10 into 10 into 10. Okay. And why product? Because, well, I don't know. Does anyone want to jump in? Why the product? Why aren't we taking sum or any such thing?
Product rule.
We fix one position
For
and then
each
there is
pair, we are all the choices are there. So
Okay, so it's like you fix for the first component, you take any one of the 9 choices, and having fixed one of those choices, the second place can be chosen independently, right? You have any of the 10 choices are available. So for each one of the 9 choices, there are 10 possibilities for the second. So totally for the first two, we have 9 into 10, 90, and so on. So the same logic. So in some sense, what we are doing here is really, these 4 positions are being filled independently. Okay, so this is independent choices. It doesn't matter what I filled in the first place. I have 10 choices for the second place and so on. Okay. Okay, great. So how many of these numbers are even?
the unit place we have to fix to 0, 2, 4, 6, 8.
Okay,
5
great.
choices. So that's we have to change.
So the same logic as before. Now here I don't have all 10 possibilities. I can only allow 0, 2, 4, 6, 8. So that's 5 choices, right? So I have 5 choices for the units digit, and all the others were as before. So here I have 9 choices, 10 choices, 10 and 5. So the answer here is 9 into 10 into 10. And the last digit alone is a 5. So I have those many choices. Okay, great. Now let's ask another question along the same lines. How many 6-digit numbers are there? Okay, all of whose digits are either 1, 2, 3 or 4. All digits?
4 power 6.
Okay, great. So it's 4 power 6 for the same reason that we talked about earlier. There are 4 choices for each digit. They're all independent choices. You can choose them independently. So this is 4 power 6. Okay, now here's a question which is sort of related, but not outwardly so. So let's take a set. So let S be a finite set. How many subsets does it have? Let's say the cardinality of S is n. What is the cardinality of its power set, which is the set of subsets? What is the cardinality of the power set of S? Okay, so
2 power n.
2 power n. Okay, why is this 2 power n?
Every element having 2 choices, either in a set or it is not in a set.
Okay, great. So every element can either be in the set or in the subset or not in the subset. Therefore, there are 2 power n choices. Okay. So another way of stating this is to say you could take the elements of the set S. So you can write the elements as A1, A2, A3, AN. I'm just calling the elements of S as A1, A2, A3, AN, and a subset T of S. So just to rephrase what was said, you have 2 choices for each element of the subset. So let's suppose T is a subset. I can construct a string of zeros and ones as follows. If A1, the first element, belongs to T, I will put a 1 there. If it doesn't belong, I'll put a 0 there. So for example, if A1 is in T, I can put a 1. Suppose A2 is not there, maybe A3 is there, and so on. Maybe AN is not there. So in a sense, a subset of S can be encoded as follows. You can think of it as a binary string, a string of zeros and ones of length n. Okay, so this is another useful thing to keep in mind. Not just the cardinality, but the power set of S itself can be thought of. I mean, there is a bijective map or a one-to-one onto map from the power set to the set of all binary strings of length n. Okay, binary, of course, just means you have zeros or ones, and then that's like the previous problem that we just talked about. Okay, so I have a binary string which can have n places. Each place has two choices, 0 or 1, 0 or 1, and so on. So the total number of choices is 2 power n. Okay, so that's also the power set of S. Okay. So this is all of these were really instances where the choices were independent. So here's problem 2. Okay. So let A and B be 2-digit numbers. So give you 2 of them, and with the following property, whose product has units digit 2. How many such ordered pairs AB are there? So I hope the question is clear. So what I'm saying is, so A is a number, it has 2 digits, B is another number with 2 digits, and when I sort of perform the multiplication, the answer ends in a 2. Okay, that's the unit digit. I of course will have more digits, but I'm asking how many pairs of numbers, 2-digit numbers AB are there, such that when I multiply them, the product will end in a 2. So what should I do first?
So we have to count the number of 2 digits. The last digit should be 2 or 6. Again, we have to find the number of 2 digits. The last digit 6 are undertake the product.
So when you say last digit is 2 or 6, which digit do you mean? You mean this one? This?
So if we take A, yeah, that one last one.
That last digit should be a 2, digit, and this should be a 6.
This is 6. Yeah.
Okay, so maybe we'll just call these last digits as something, because of course those are the 2 numbers which determine what the last digit of the product will be. So I'll call this last digit as what you call P and Q. Maybe. Okay. So you're saying that the only way in which this can happen is if P equals 2 and Q equals 6. Is that right? Is that
yeah, and P equal to 6 and Q equal to 4.
Okay, wonderful. So let's see. So you already found another one, P equal to 6 and Q equal to 2. Okay. Any others?
1, 2, P equal to 1, Q equal to 2.
Right. So you already see there are many more actually. P can be 1 and Q can be 2.
3, 4.
4.
Okay. So now that we start looking, we find many more. So maybe we first have to let's tabulate this in some fashion. So let me just get rid of this for a second. So let us. So okay, so let's write down the possibilities for P, and against each possibility for P, we will see how many possibilities there are for Q. Okay, so I'll just put some sort of table P, Q. Okay, so can P be 0?
No.
No. Okay. P can be 1, and if P is 1, what is Q?
2.
2 is the only possibility, right? Okay, now let's go to the next. If P is 2, what is Q?
1.
Or
6.
Okay, so actually there are 2 possibilities, 1 or 6. If P is 3, then Q must be
4.
Okay, any other possibilities?
No, sir.
No? Okay. Yeah, there are no other possibilities. If it is a 4, then
3.
3, that's the only possibility. If it is a
8.
5,
Oh, 8 also.
8.
8. Oh, sorry. Yes, there is also 8. Absolutely, I missed it. 3 or 8. If P is 5,
No,
For the
sir.
3, sir, for the remaining the
There are
previous
no
one.
choices.
For 3, we have 4 and 8. No.
for 3 you have 4 and
Yeah. No. 4.
Only 4.
only 4, right? You can't get 8 for 3. Yeah, that's only there for. So there is some slight loss of symmetry. It's not quite the. Yeah. Okay. So what's the case for 5?
Nothing, sir.
Okay, you can't have 5.
Yes.
6.
2 and 7.
Okay, 6 2s are 12. 6 7s are 42. Okay. 7.
6.
And that's all. 8.
4.
Any others?
4.
9.
9.
9.
Yes. And if it's 9,
8.
8. That's the possibility. Okay. So here is a instance of a counting problem, which what was our very first step? What we have done is really sort of split it into a disjoint union of cases. Okay. I mean, we have considered cases. So these are all disjoint cases, right? If P being 1 or P being 2, P being 3, and so on, they're all different cases. Okay. And what we are noticing here is in some cases, Q only has one choice. In other cases, Q has two choices. Okay, but of course, this is not the full solution to the problem. We still have to go back and solve the original one, right? So this is only P and Q. What about how many choices there are for A and B in each of these situations? So let's just focus on one of them. So let me take the very first one. Okay, so P is 1, Q is 2. Okay, so which means that I'm looking at an equation like this. I'm sorry, a multiplication like this. P is 1, Q is 2, but I still don't know what these stars are, right? I have choices for them. So how many choices are there now for A? So this is the case I'm now doing. Choices for A.
8 choices.
9.
Number of choices equals
9.
9. Why 9?
Except 0, we can take it.
Yes. So it's only the tens digit which I have to decide, and there are except 0 I can pick any other. And number of choices for B is again
9.
9.
Right. So in case 1, when P and Q are both 1 and 2, the total number of choices for A, B will become 9
81.
times 9, which is 81.
81.
So here the total is 9 into 9, right? So these two tens digits can now be chosen independently. I mean, there is no dependence relation of them. I choose any one of the 9 for the first guy and any one of the 9 for the second. Okay, so I've sort of figured out that for this very first case, there are 81 possibilities. How about the second case? Suppose P is 2. Okay, so I'm going to take a case when P is 2. Now in this case, how many choices for A and how many for B?
A, 9 possibilities.
For A, there are still 9. For B,
So we have to use inclusion.
for B,
1.
what do we have to do?
6.
Uh,
1 and 6.
Again 9 plus 9.
So again
18.
9 plus 9.
18 now.
18.
Yeah, absolutely. So observe, this is now 9 into 2, 9 plus 9, if you wish, because the units digit of B can be 1 or 6 here. There are two possibilities for that. So the units digit itself is, so this is, we are in case 2, right? So this is a 2. So I'm asking, okay, if this is a 2, then what are the possibilities for the other 3 digits? So this other units digit is 1 or 6. Okay, and these two tens digits, there are 9 possibilities. Okay, so basically for A you have 9 choices, for B I have 18 choices. Okay, so what does that give me in this case? Therefore, total number of possibilities for
9 into 18.
9 into 18. Okay, now what about the others? what about the remaining cases?
3 and 4, it is 81 again.
Okay, 3 and 4, it's
Again 81.
like the very first
Yes,
case
yes.
that we did, right? So that's like 81. The next one is like
9 into 18.
9 into 18. Okay. So what we notice is once you've done the first two, then the rest are actually part of the same pattern. Right? You can just figure out what the rest are. So let's just compute the final answer just for fun. So the total number of cases which are like the first case, there is only one choice for Q. So that's 1, 2. How many are like that? 3. No.
4.
For odd cases, only odd numbers. 1, 3, 7.
Oh, wonderful. That's just for the odd numbers. 1, 3, 7, 9. 5 was missing. Okay, and then the even numbers 2, 4, 6, and 8 have two possibilities.
4 times.
4 times. Okay, so the total number in this case, let's complete the calculation. So the total therefore is 9 into 9. There are four such possibilities. 9 into 18. There are four such possibilities. And then what I'm doing here is adding these together.
Yes.
Right? So we have all along until now we were looking at instances where there's multiplication, but now I have to add. And why is that?
That is a separate one.
Different cases.
Correct. So this is so I mean these are all separate cases, right? So I'm sort of taking many disjoint cases, and when I have written my problem, decomposed my problem into a sum of disjoint problems, then I count each of them separately, and then I can add all of them up. Okay, so that's the answer. Okay, so whatever that works out. Okay, so good. So this is we have now seen an instance of both principles. So there are two operations which you tend to see when you try to count configurations of various kinds. One is multiplication, the other is addition. So here we saw an instance where we have to use both. You multiply inside each subcase, right? Because there was some independent choices involved there. So we used multiplication to figure out how many configurations there are in that subcase. But then the final answer is obtained by adding all the subcases together. Okay. So that's a nice problem to which demonstrates both these operations. Okay, so let me move on to the next question, which must be extremely familiar. How many permutations are there of the numbers 1 to n?
N factorial.
N factorial.
N factorial.
Okay, so n factorial, which is of course just 1 into 2 into 3 to n. Again, this is an instance of the multiplication rule at work. So we have a permutation is just a way of arranging the numbers 1 to n in some other order, right? And the way we reason to say it is n factorial is to say, well, look at the very first element in the sequence. That element can be chosen in n possible ways. So this has n choices. Here we can allow any one of the numbers from 1 to n. But having chosen the first element, the second element has only a reduced number of choices, right? So here, this is what you would sometimes call sort of dependent choices. These are not independent choices, as in contrast to the earlier examples. Here, the second digit, what you choose, depends on what you chose in the first one. But there is still some nice uniformity here. No matter which first digit you chose, the number of choices for the second digit is the same, right? So how many choices are there for the second digit? Well, you can allow any one of the n-1 remaining digits. Remaining numbers. So this is what you might sometimes call dependent choices. But there is some uniformity here. However, there is a certain uniformity, which is that no matter what number I pick for the first component, for the first digit, the number of choices at least is the same. Even though it depends, the actual choice that I can make there will depend on what I put in the first one, but the number does not depend. It's always n minus 1. And having chosen the second digit, the third digit can be chosen in n minus 2 ways, and so on. The fourth digit can be chosen in n minus 3 ways, and etc. And that's how we prove the fact that the number of permutations is n factorial. Okay, so let's do another one which is uses the same principle. So this asks, so take a convex polygon. So convex polygon is, it's like the various things one is used to seeing, like, so here's an octagon, for example. It need not be regular, so I'm just drawing just an octagon here. So it has 8 vertices. So in general, let's take a convex polygon with n vertices. So the question is, how many diagonals does it have? And a diagonal, by definition, just like for parallelograms or other polygons, is something which connects, any one of these is called a diagonal. So there are many diagonals in general. So the question is, how many are there? I mean, they need not all pass through the same point if it's not a regular polygon. So how many diagonals are there?
8.
For an octagon, 8 is for the octagon, or what is the proposed answer?
N combination of 2 minus n.
I'm sorry, what?
N combination of 2 minus n.
N combination of 2, sorry,
Minus
n combination of, n combination?
NC2 minus n.
NC2 minus n. Okay, why is this?
Because I'm not considering side as a diagonal.
Okay, fine.
So that's
Okay.
why.
Okay, sounds good. Yeah. So let me sort of rephrase what you just said in a different manner. So what is a diagonal really? A diagonal is actually a choice of 2 points. So I should think of a diagonal as being, when is a diagonal obtained? If I tell you, if I make 2 choices of A and B, then that determines a diagonal. Okay. So how many choices are there for A and B? That's basically the question. So the point is, there is a certain dependent choice here. Okay. So let me try and choose a diagonal as follows. I will choose A. So let's number the vertices maybe. 1, 2, 3. So in general, these vertices will go up to n. Okay, so I have n vertices. Now, when I choose A, can be any one of these n vertices. So A has n choices. Okay. Now, having chosen A, so let's maybe choose A to be one of these guys. Suppose this is my A. Having chosen A, since I want a diagonal here, what are the choices for B? Okay. B, of course, cannot be A itself. B cannot equal A. That wouldn't give me a diagonal. Just give me a point. But there are two forbidden choices. Yeah. How many choices are there for B if I want to get a diagonal?
N minus 3?
Yes, it's n minus 3. Okay, because not only is A itself forbidden, the 2 neighbors of A are also forbidden. Okay, so the choices here is, no matter what I pick for A, the number of choices for B is the same. Okay, so it is dependent, of course, on A, but the number is the same. So there are n minus 3 choices, and so the total number of possibilities for the pair AB is n into n minus 3. But of course, AB and BA are really the same diagonal, right? So if I sort of look at this number n into n minus 3, what I would be doing is I would be double counting, because say suppose I chose this as A and this as B, But then I could have also chosen B as A and A as B. Right? I could have chosen the same diagonal using the other the points swapped. And if I do that, then of course I get the same diagonal. So the total number is, well, it's really this, but up to a factor of 2. There is a double counting which I have to account for and correct for. So the total answer here is n into n minus 3 by 2. And this is actually the same as the other proposed answer, because I can rewrite this as follows: is n square minus 3n. So I'll rewrite it like this: n square minus n minus 2n divided by 2. And that's really n square minus n by 2 minus n. And this first thing is what you probably know as NC2. Okay, we'll come back to NC2 and so on later on. So these answers are the same. So this again is obtained by the following argument. You pick any two unequal vertices. The number of choices is NC2, but that gives you, well, it can give you either a diagonal or it can give you a side, because you may have picked two adjacent vertices. So this minus n just removes the sides from this calculation. Okay, so there are usually many ways of getting to the same answer. So I hope this answer here is clear. It's n into n minus 3 by 2. Okay. So this again is sort of an example of dependent choices. So let me go to the next one. Problem D. How many 6-digit numbers how many 6-digit numbers are there which have no two of whose consecutive digits are equal? Okay, with the following property. No two consecutive digits are the same. Okay, so what I mean is, so for example, here is an example of a number that's not allowed. So suppose I have 2, 3, 1, 1, 4, 6, for example. So here's a 6-digit number, but I have two consecutive digits which are the same. Okay, so two ones appear one after the other. So similarly, nowhere in this number should I have this sort of configuration. Two consecutive numbers being the same, that's not allowed. Any thoughts on how we would, this is not allowed. How would we approach this problem?
We have to find the number of consecutive digits.
Sorry?
So we have to subtract from the number of 6 digits minus number of 2 consecutive digits.
Okay. Total number of, so you are proposing to solve the complementary problem, which is find the number of numbers which have 2 consecutive digits. Okay, we could do that, but how would you do that? We want, so you could be a slightly more complicated problem, because there will be many more configurations. There was another suggestion.
So first we can fix 9 choices. The next we have to remove the 2 consecutive numbers, means the previous one and the next one.
No, not like that. Two consecutive numbers. No, two consecutive digits. See, all I'm saying is no two consecutive digits are the same. So 2 followed by 3 is okay. That's not a problem. What I'm saying is that if the first digit is a 2, the next digit cannot be a 2 also. So these are two consecutive places have the same number. Sorry, maybe it's not very clear the way I have phrased it. Yeah, this is what I want to capture. I want to say two places cannot have the same number. So I have 1, 2, 3, 4, 5, 6 digits. So what's the suggestion?
We rename it that two digits some stars. So we have to ready to 5-digit numbers. You got to rename it as some star for 2 consecutive digits. Maybe we can consider about the 5-digit numbers.
So what should I? No, but I don't want them, or do I want them? Which problem are you trying to solve?
I'm using the complement.
Complement. Okay. So what do you want? You say, okay. So here are 2 consecutive digits, and
so we rename it. We consider as a single digit.
Yeah. Think of it as a single block, single digit, and think of it as a 5-digit number.
Yeah. Now we can find the number of 5 digits. And then we have to subtract from the number of 6 digits.
Okay, so that's a very good thought. The trouble with that is the following. What about, so you also have to look at these other ones. No, the 2 consecutive digits can occur anywhere else, here also. What if your consecutive digits are in the 2nd and 3rd places? Still, you can do the same thing. Think of it as a single block, and just think of what's here as something.
Again, it is a 5-digit number.
Again, it's a 5-digit number, and then count the total number of such numbers, right? So the trouble is the following. Suppose I have the following number 1, 1, 1, 2, 3. Okay, so look at this number 1, 1, 1, 2, 3. Now, what's the consecutive string here? So the first 2 digits both are ones, right? So you will sort of get this number 1, 1, 1, 2, 3 will occur when you do the first case, when the first 2 stars are equal. So these are both ones now. So you will think of that as a single block, and it's like 1, 1, 1, 2, 3, right? So you are counting that number once in case A. So let's call this case A. But you're also counting that number once in case B, because here again, the 2nd and 3rd digits are also equal to each other. So I might have thought of this very same number as like this 1, 1, 1. Sorry, how many digits do I have? I only have, sorry, I missed a digit. Let's put 4 there. 2, 3, 4. So the very same number would also get counted in case B. Is this difficulty clear?
Yes.
So,
yes, sir.
So the idea is very good. The trouble is there is a lot of over counting involved here. The same number, when the repetition is more than just 2 digits, when you have 3 consecutive digits are equal, then you'll have a lot of over counting. Okay. So of course there are ways of trying to correct for the over counting and so on. But this approach is slightly more involved. We'll have to work a little harder to get this to work.
Sir?
Yeah.
Is it 9 power 6?
Okay, the answer is right. How did you get this?
So I think we have to go gradually. So the first digit can be filled in 9 ways, because
first
it can
digit matlab from which side?
From left side.
From the left side. Okay, so let's do this. 1, 2, 3, 4, 5, 6. There are 6 digits in this number. So let's solve the original problem. No 2 consecutive digits are the same. Choices, because it can be any number from 1 through 9. Okay.
Yeah. Now we don't want the consecutive digits to be same, so we'll just exclude the first digit. And now we have 10 choices. Out of 10, we exclude 1, which we already took in 1.
Sounds good. So suppose the first digit I can fill any one of these numbers. I fill A as my choice. Then the second digit, well, originally I had 10 choices. I can allow any number from 0 to 9. But this additional constraint says that I'm not supposed to take A cannot occur again as a second digit, right? So allow 0 to 9, but exclude A. I can allow any one of these 10 choices other than A itself. Okay, so if I do this, then how many choices are there? So there were 9 choices for the first digit, and there are now 9 choices for the second digit. And then you do the same thing. So second digit you have chosen to be one of these 9 possibilities from 0 to 9. But having chosen the second digit to be B, the third digit, again, you have originally 10 choices, 0 to 9. But then the B that you have already chosen, that you must exclude. So that you exclude B alone. So you still have 9 choices. Okay, and so on. So now if you proceed from left to right, what one obtains is that there are exactly 9 into 9 into 9, 6 times, which is 9 power 6 choices. So the answer is 9 power 6. Okay, is this okay? I hope this is fine. Okay, so I have a question. So we started from the left, right, and reasoned that the answer is 9 power 6. But what if we had started from the right? So suppose I had done the very same problem, 3, 4, 5, 6. Okay. But I now want to redo the problem starting from right to left by looking at how many choices there are for each digit coming from the right. Okay. So let me start. How many choices for the rightmost digit? 10 choices. Okay. Now, having chosen the rightmost digit to be something, let's call it A, the preceding digit can be any one of the 10 numbers other than A itself, right? So I have to exclude A. So therefore, there are 9 choices. Same logic as before. So 10, 9, 9, 9, 9, 9. Do we get a different answer?
So, no, sir, it's not 9.
Sir, we have to
For third digit, we have 10 possibilities.
Sorry, what? Third digit, you still have 10 possibilities. Here,
yeah. Yeah.
Why do you have 10 possibilities?
Maybe we call B. The second is B.
Okay.
Except B, we can allow anything.
Correct, but except B, you can allow anything means only 9 possibilities, no?
So there are 10 possibilities. Okay.
So B is removed. So only 9 possibilities.
Yes, yes.
So you have it some number. You chose some C. Having chosen C, the next digit to the left, there are 10 possibilities other than C, and so on. So why do I get a different answer?
Sir, you have to exclude 9 power 5, right? Because the leftmost digit can have 0 as well, no?
Okay, wonderful. So I sort of did it very cavalierly. There is some problem with the leftmost digit. This, of course, cannot have a 0 in it, right? So how many choices for the leftmost digit?
So you can fix the leftmost digit 0, and then
8.
no, that's not right.
The previous to the leftmost, based on that, the choices will be there in the leftmost.
Okay. So what does that become?
That means suppose the previous to the leftmost is 0 means.
Okay.
Here we are having 9 choices.
So let's call this E now. So what are you saying? So if E is 0.
Yes.
So observe the thing that there are only 8 choices here is not always true. It's only true when depending on what E is. Okay, so there are actually 2 cases here. So let's do case 1. So what are you saying? If E is 0. Okay, then let's call this digit F. So do you want to do E equal to 0 or E not equal to 0 first? Shall we do E equal to 0?
Yeah.
Okay, so if E equal to 0, so that's my first case. So in this case, then How many choices for F? F can be any
9
number.
choices.
F can be any number from 1 to 9, right? F belongs to the set 1, 2, 3 to 9. So there are 9 choices here. Okay, so if E is 0, there are 9 choices. If E is not 0,
8 choices.
then there are only 8
8
choices.
choices.
Right? So then F can be any one of these numbers other than E. So I have to subtract, delete E from that set. Okay, so there are only 8 choices. Okay, so how do we find the final answer?
For
So
each
9
choice
power
we
6
have
is
to.
right.
Yes. For E equal to 0 choice, we are having 8 into 9 into 9 to
9 power 5 into
9
10.
power 5 into 10
Plus 9 power
plus 8 into 9 power 4 into 10.
Sorry, why is that? Sorry, I lost you. What was the first case? In this case, how many are there? So you're
9
saying
power 4.
9 power 4
9 power
into
5.
10.
9 power 5. For first
5
case.
into 10. Yes. 9 power 5 into 10.
9 power 5. Oh, sorry, I shouldn't put this here. Okay. Why 9 power 5 into 10?
If E equal to 0, the first choice we have 9 choices. For F,
Yeah.
Oh, only 9 power 4, sir. Only one, sir. E equal to 0, that is fixed, no?
Yes. So you have
9 power 4
made
into
a
10.
choice for E.
Yes, sir.
So E equal to 0. So let's do this. Let's do it slowly. So this E equal to 0 means what? So 1, 2, 3, 4, 5, 6. E I have put as 0. This is any number F. Then A, B, C, D are only there. A, B, C, D. Okay. So now how many possibilities? 9 power?
4 into 10.
9 power 4. 9 power 4. Why? Because?
For F place 9 choices. D place 9. C and 9. B is 9. A is 10.
9 power 4 into
10.
10. Okay, fine. And case 2?
Plus
8
into 9 power 3 into 10.
So for E, there are, E is not 0.
0. That means 1 to 9 is possible. Yes.
There are 9
8
choices.
into 9 power 4 into 10. Yes.
8 into 9 power 4. Okay, so for E, you're saying now there are 8 choices. Why 8 choices?
9 choices, sir.
9
For
choices.
F place, it is 8 choices.
F it is 8 choices. Okay, sorry. 9 choices, this is 8 choices, and then the remaining are 9, 9, 9, 10. Okay, so how much is that? 9 power 4 into 8 into 10. Is that all right?
Yes.
Okay, so let's add them together. So the sum, total number of possibilities is 9 power 4 into 10 into 8 plus 1. So I think of it as still a different answer, right? This is not 9 power 6. It's actually 9 power 5 into 10. So there's something wrong somewhere. We have to think about where so you can already see counting is can be rather confusing at times. So let's see. There must be some flaw in the argument somewhere. Anybody find the flaw here?
Choice of E in the second case.
I'm sorry, what?
Choice of E in the second case, sir.
Choice of E in the second case, okay.
It not be 0 and it not equal to D also.
Cannot be 0. It's also not equal to D. That's correct. Yes. Correct. Okay. So exactly. So observe we are sort of arguing from right to left, right? So which means we have first chosen A, There are 10 choices for that. Then chosen B, then chosen C, then chosen D. Then we have come to E. Okay. So the point is, well, in fact, what it says here is that, so okay, so let's look at the second case. How many possibilities are there for E? Well, E can't be 0, but E also cannot equal D. Right? So in this case, how many choices do you have? You don't have 10, it can't equal to 0, it can't also equal to D. So what does that mean? How many choices do you have?
8 choices.
Well, what if D is 0? So now the problem shifts even one further step to the right. Right? What if D were 0? If D is 0, then there are 9 choices, because
this will not
it's
end
not.
until you reach units place.
I'm sorry, what?
This process will not end until you reach units place.
Right, exactly.
D
So the
can be
point
0, then
is,
C can be 0, B can be 0, A can be 0. So I
absolutely.
have one better way. What we can do, we can fix F to be 0.
Okay.
Find number of possibilities and subtract it from 10 into 9 power 5. That's it.
Sorry, say that again. You can take the
So
case
we
where
found number of possibilities as 10 into 9 power 5, right? Without considering 0 case.
without considering 0 case. What do you mean?
Yeah, I mean.
Acha. You mean in the original? Yes. We found it to be 10 into
9 power 5. Yeah, here.
Okay. Yes. 10 into 9 power 5. Yes, correct.
So fix F equal to 0. So you will have total 9 power 5 cases. Subtract those cases from 10 into 9 power 5. You have your answer.
Okay, fine. Sounds good. So you sort of want to modify this. So let's take your suggestion. So if you sort of do it from right to left, then what are the possibilities? The total we got was 10 into 9 power 5. Okay, because we said there are 9 choices here, and then there are 9 choices for F if you also allow 0. So this is now also allowing 0. This is sort of a extra thing we were doing. That's why we got an overcount. But then having overcounted, let's correct for it. Let's subtract out the overcounting. So minus the case where F is 0. The numbers which are
F cannot be 0.
So sorry, what?
F cannot be 0 because we are considering 6 digit.
Correct. But see, this count here, this first answer we found is actually an overcount. It's an overcounting because here we are also allowing F equal to 0. So maybe let me just explain that once more. So see, this right to left argument is the following: 3, 4, 5, 6. There are 6 digits. For A, there are 10 choices. Having chosen A, for B, there were 9. For C, there were 9. D is 9. E is 9. And then F, if you now relax it a little bit, say, okay, F can also be 0. I will also allow that. Then there are 9 choices for F also. Okay. So this is the total under this relaxed assumption. So here it's an overcounting. So now we say that so the number of choices here in which F is allowed to be 0. So this is now 10 into 9 power 5. But this is not what we want, because this is not only 6-digit numbers, it also includes smaller, less than 6-digit numbers. Right? Okay, so we don't want that. So what we do is we say, okay, 10 into 9 power 5 is no overcount, but from that, let's get rid of the bad guys, which is the numbers in which F was actually a 0, the number of choices in which F is a 0. Okay, now how many choices have F equal to 0? So let's see, how many choices have F equal to 0? How do we find that? So it's like saying now instead of a 6-digit problem, the very first digit is gone. So F is gone. Let's get rid of F. Now I only have this. So how do we solve this one? Any suggestions?
again we can solve it from left to right. And
Okay,
if
that's
not,
sort of
then again the same process.
okay, right. So if you solve it from left right, that's cheating because we have sort of we didn't want to do that. But what you could do is to try doing the same thing again. Okay, so let's imagine we only know how to do things right to left. So again, you could say, okay, how many possibilities are there from here? Okay, sorry, just a second. So if f is 0, but what about e being non-zero? I suppose we are assuming E is non-zero in this case. Okay. Yeah. So okay. So in some sense, what you will have to do really is try, just doing the same thing again once more with 5 digits instead of 4 digits. Okay. So it's from here. It's 10 into 9 power. Sorry, instead of 9 power 5, it is 9 power 4, and then so on. So okay. So and so on. So this and so on is the tricky part. Minus 10 into 9 cubed minus. So each time I need to put this bracket. Okay, and so on. So I'm going to leave this for you to try out maybe. So the point here, I mean the reason for my bringing this up was really to say that sometimes these reasonings can be rather subtle. Okay? So especially when there are dependent choices. So it depends on what happens in the preceding step. So the problem here was really the following, that in some sense, every digit only influences its neighbor, right? When you go from right to left. So things were moving along smoothly until we reached the end, because at the left end, there was an additional constraint, which is that digit cannot be a zero. Okay? When you did this from left to right, you were sort of okay, because at the very first step, there was some constraint that you can only have 9 possibilities. But after that, every digit only influences the digit to its right. So you only sort of get, just the simple dependence relation. So here the dependence propagates, and then at the end, there is one additional dependence which comes into play. And these sorts of things keep, happening in more complicated problems. So here's an exercise problem for you to think about. See if you can, sort this out. Just do it only right to left. Okay, the entire problem done right to left without ever using the left to right. Okay, so let me move on. Let's look at. Okay, so let me go to the next problem, which is problem 3. So let me say, how many numbers from 1 to 1001 are divisible by 7?
So integer part of 1001 by 7.
I'm sorry, what?
Lower integral part of 1001 by 7.
Integer
Okay,
part of
1001 by 7, right. So 1001 by 7 integer part, 1001 is actually divisible by 7, which in this case is, let's see, 7 1s are, 4s are, 3s are. Okay, so in fact 1001 is 7 into 11 into 13. Okay, so this is actually 11 into 13 here. So the number of numbers divisible by 7 is just 11 into 13. So but of course that's not my eventual question. So I want to ask, how many are divisible by 11 similarly? So question A, how many are divisible by 7? B, how many are divisible by 11? That's again the same sort of computation. So the answer is 1001 by 11 in this case. So it's exactly divisible. Give me 7 to 13. But the thing we want to do, and which is sort of related to our previous problem, is, suppose I say things which are divisible by 7 or 11.
You have to use the inclusion and exclusion principle.
Okay. So what does that mean?
So we consider A as set of all numbers which is divisible by 7. B is a set of all integers divisible by 11.
Okay. So let me maybe call it A sub 7, which is set of all m from 1 to 1001 m to n, which are divisible by 7. M is divisible by 7. And A11 similarly divisible by 11. And now what we are asking is how many are divisible by 7 or 11, which means we are asking for the set which is the union of these two sets. So I want to know what is A7 union A11. Right? That was my definition. Okay, A7 and A11 are the multiples of 7 and 11. So my question is, what's the number of elements in their union? And so now we sort of use this classic set theory thing, which says that if I have two sets whose union I want, so this is my ambient set, and I want to know how many elements lie in the union, we just take A7, so the cardinality of the union is just the cardinality of each set minus the cardinality of the intersection. And so we know each of these two answers, A7 and A11 are known. So this is just, this was 1001. Yeah, this was 1001 by 7. This was 1001 by 11. And now here, things which are divisible by both 7 and 11. So what's that?
The LCM of some.
Right. So LCM 7 and 11 are both primes. So if a number m is divisible by both 7 and 11, then it must be divisible by their product, which is 7 into 11.
77.
It's divisible by their LCM, which is 77. So this answer similarly is all multiples of 77. So this is the answer. 1001 by 7 plus 1001 by 11 minus 1001 by 77. Okay. Now, of course, one has this. This sort of principle is called the inclusion-exclusion principle, which is you sort of overcount initially by saying, okay, I'll take the entire set A7 plus the cardinality of the set A11. But when you do that, you're double counting the elements of the intersection. Right? So then you subtract them out. Okay? So you first include it, overcounting, and then you exclude it. And this principle, of course, generalizes to a union of any number of sets. So if I have, say many sets, let's call it some other name, S1, S2, S3, and so on. So I have collection of finite sets whose union I want to count. I mean, the cardinality of the union I want to find. Then I first take the sum of their cardinalities, 1 to k. But then this will double count the intersections. So I subtract out the intersections. All SI intersection Sj. Okay, so here what are I and j? I is, I and j are disjoint indices. So I and j go from 1 to k, but I is not equal to j. Okay, maybe I shouldn't call this k here. Call this n. Ij go from 1 to 2. But then this is again because I have subtracted all the intersections. What I have done is corrected for it too much. So I have to I have excluded too many, the triple intersection. They have a three-way intersection that has now become excluded a bit too much. So I have to put it back in. So it's a plus the cardinality of threefold intersections, SI intersection Sj intersection Sk and so on, minus fourfold intersections, etc. till I run out of the last term will be the intersection of all the n terms together. So this is the general principle, which is extremely useful. And so, for example, this is used to, almost as a generalization of what we just saw. You can use it to, count, for example, things which are divisible or not divisible by various numbers. And so here is an application of this principle that we just saw. It's called Euler's torsion function. So here is the definition. Some of you might probably have seen this before. Euler's torsion function is the following. It's a function on the natural numbers. It's a function from the natural numbers to the natural numbers, defined as follows. Phi of n for a natural number n is the number of numbers. So this is the number of m. So maybe you should just call it the cardinality. It's just the cardinality, the size of the set of all numbers m from 1 to n, which are relatively prime to n. So GCD of m and n. Getting these various lines. So just a second. Still have it. Sorry, just let me just relaunch this. Seems to be no way around. Okay, so maybe I'll just carry on. Is my screen still visible?
Yes, sir.
Yes, sir.
Okay. So are you also seeing these funny lines on the top?
Yes, sir.
Okay. I have no idea why that's happening. Okay, so that's it. Okay, can you see my thing still? Is this notebook thing clear, visible?
Yes, sir. Visible.
Yes, sir.
Okay, fine. So, okay, let me just repeat what I said at the end. Euler's torsion function is a function on the natural numbers defined to be, for each natural number n, this is the number of numbers from 1 to n, which are relatively prime to n, GCD of m and n is 1. Okay, so, for example, if you take n equals 6, for instance, so what we are doing here is looking at the numbers 1, 2, 3, 4, 5, 6, numbers from 1 to n. And out of these, we are just trying to see how many are relatively prime to 6. So, for example, the numbers here are 1 and 5. They are the only two numbers which are relatively prime to 6. So, phi of 6, for example, is the number 2. Okay. Now, what we've just done, this computation with 1001, for example, it demonstrates this general sort of principle. So what you could do is use that idea to compute this function phi, okay, which is what Euler did, and got a formula for phi. So the formula is the following. Suppose I take suppose I take n, my natural number. Any number can be factorized into prime factors. So let me write it as P1 to the K1, P2 to the K2, and so on. PR to the KR. So PIs are some prime numbers. And KIs are all the exponents, the powers, which are at least 1. Okay. So now I have, well, I need to compute phi of n. So what does phi of n mean? I need to look for numbers from 1 to n whose GCD is 1. Okay. So what does that mean in terms of these prime numbers Pi? So if I say m is a number whose GCD is 1 with n.
So all the powers of the m should be 0.
All the powers
Again, we have tried the m as a product of prime powers.
Okay.
And then we take the minimum power of each. P1 power minimum of.
Correct.
Suppose.
Yes, correct. So the GCD is just I take P1 to the minimum of K1 and the power which divides n. Yes. But that power should be 0. That's what GCD being 1 says. So what does that mean? Does the prime P1, will it occur in the prime factorization of m?
No, sir.
No.
It doesn't, right? It occurs with power 0. That's what.
Any PIs does not occur in m.
Correct. So the PIs do not divide m. So this is just notation for that. PIs do not divide the number m. They don't occur as prime factors of n. So m is not a multiple of any one of the PIs. Okay, for all these numbers from 1 to k. So what does that mean? So now it's again a counting problem of the same kind that we have solved. We want to count how many numbers between 1 and n have the following property, that they are not multiples of P1, they're not multiples of P2, and so on. Okay. So the inclusion exclusion principle is similar. So now what we'll do is we'll say let Si denote the set of all numbers m from 1 to n, which are let's say not multiple, or which are multiples of Pi, for example. So I mean we could define it in different ways, such that m is a multiple. So let's do it using the complementary. So let's take the set to be the numbers which are multiples of Pi, and now we'll use the inclusion exclusion principle. So in other words, if I try to compute the union of these sets, okay, so let's consider the union of the Si. What does that mean? The union is it's all those numbers which are divisible by at least one of the Pi's. Right? So the union of the Si's from 1 to r here, right? I goes from 1 to r. The union just means it's all those numbers m, such that m is a multiple of at least one of the Pi's. In other words, it's those m's whose GCD is not 1. It's the complement of the set that I want. Okay. So if I know the cardinality of this set, I can just say n minus this cardinality. That will give me the cardinality of the other set, the complement. So let's compute the cardinality of Si, union Si. So what is this?
Summation of integer part of m by p.
Okay, first I have to sum the cardinalities of the Si's, but then from that I subtract out the cardinalities of two-fold intersections, and then add the cardinalities of three-fold intersections, and so on, etc. So let's just do it. So the first sum is what? Si is multiple, so it's integer part of n by Pi, but remember Pi divides n. So there's no integer part is not equal. It's just n by Pi in this case.
M by P.
M or n? N.
Yeah.
See, m is just it's a set of all m such that m goes from 1 to n and m is a multiple. M is just a free variable. So, okay. So now I have n by Pi. That's a summation of the cardinalities of the Si's. And from that, I need to subtract out the cardinality of two-fold intersections. So what is SI intersection SJ here? What is that?
It's an empty set.
Why is it the empty set?
Because PIs are disjoint primes.
They are disjoint primes, but what does that mean? SI intersection SJ means I'm looking for all those numbers n from 1 to n such that m is a multiple of pi, that's pi divides n, and pj also divides n. Right? The primes are disjoint. See, if I have 2 and 3 are my 2 primes, 2 divides m and 3 divides m, of course, there are many such numbers which are divisible by both 2 and 3. Right? So what does this imply? If 2 different primes divide a number, then that's if and only if their LCM divides.
Product.
Which is the product in this case. The product, which is pi pj, should divide that number. Okay. So therefore, what is this two-fold intersection?
N over pi pj.
Exactly. So this is exactly the set of all multiples of pi pj. So remember, this is the sort of computation I did with that 1001. Right? I had 1001 by 7, 1001 by 11, and then there was 1001 by 77. The same sort of thing. So this cardinality here, therefore, cardinality of two-fold intersections will just be n by the product of the corresponding primes. And similarly, product of threefold intersections just means I'm looking at multiples of pi, pj, pk, because they're all different primes. So that's again n by pi, pj, pk. Okay. So what this means finally is the following, that if I take this formula here, this is the sum over n by products of 2 primes plus summation n by product of 3 primes and so on, minus etc. Okay. So this is the formula that I get. And this is the formula for the cardinality of the union, which is, what was the union? It's the complement of the set I want. It's those numbers which are not relatively prime to n. Right? The GCD is not 1. But remember, I was trying to do Euler's torsion function, which means I want to look at the, so I want, however, phi of n, which is the quotient, the complement of this. So it is the numbers from 1 to n which are not in the union of the SIs. Right? So therefore, sorry, it's the cardinality of this set. It's the cardinality of the complement. So I must take my previous answer and just subtract it from n. Okay, so the final answer is the following. It's n minus n by pi plus n by pi pj and so on. Okay, so that's my overall answer. It will stop at some point, but I can of course pull out an n common from all the terms, right? And when I pull the n out, I claim that what's left actually has a nice factorization. You can factor it out into a nice product, and you can see what the product will be.
One minus 1 by p1.
Okay, it's 1 minus 1 by p1
into
1 minus
p2 and so on.
And so on. So observe, this is actually exactly this PR, because that's the way these terms occur, right? 1 by pi's, summation 1 by pi occurs with a negative sign. So that's what will come from the individual terms. Summation 1 by pi pj comes with a positive sign and so on. So you can see that this sum here is actually just this part. Okay. So this is Euler's formula for phi n. Phi n is just n times the product of 1 over 1 minus p. P runs over all the primes which divide n, which occur in the prime factorization of n. Okay, and what we have seen therefore is a proof of that by inclusion exclusion. Okay, so that's so we've seen a bunch of techniques so far, which is we have looked at I guess the multiplication rule when there are independent choices. We have also looked at addition, which occurs when you split the problem up into cases and then finally put them back together. Then we have looked at dependent choices, dependent but uniform, where things are still okay, you can still get it by multiplication. Then we looked at instances of inclusion and exclusion. Okay, so just one more thing that I want to talk about for today, which is, we'll eventually move on from the next lecture onwards to talking about permutations and combinations and so on in greater detail. But sort of as a prelude to that, I just want to...
So I have a question.
Yes.
So can we prove all the arithmetic function derived from the inclusion principle?
All the arithmetic function meaning?
So arithmetic function is a function from natural number to natural number. Like sum divisor or GCD sum divisor and so.
Right, yeah.
Pillai arithmetic function.
Yeah, it won't apply in all cases. So it depends on what the definition of the function itself is, right? This quotient function has a very specific sort of form which allows you to get it from inclusion exclusion. Other functions would most likely not work the same way.
Pillai arithmetic function is nothing but sum of GCD. So again we can
sum of divisors, you mean?
You want to sum all the divisors of n.
Right, the sum of divisors function.
Yeah.
So that will not quite work from this, but you can get formulas for that, using other means. By maybe similar combinatorial sorts of arguments.
So can we prove that we have to find the number of integers which the GCD should be odd?
GCD
Suppose
should be?
We fix some number, maybe GCD is odd. We have to collect all the integers m such that GCD of m comma n equal to r. We can
equal
find
to r.
We can fix r.
Yes.
So we can find the cardinality of these using the inclusion exclusion.
Yes. But this problem is actually an instance of the earlier problem, because if the GCD is r, then what you can do is you can sort of divide m and n by r. And
therefore we can prove the Pillai arithmetic function using the inclusion exclusion.
I see. Sure. Yes. But it's in some sense as it reduces to the Euler's torsion function. You can get it as
we can divide by r, we can get the GCD soon. So.
Yes, exactly. But yes, if you just want to keep it as r and you apply inclusion exclusion, that's fine. Yes, that will also work indeed. Yeah. Okay. So let me sort of ask you a question, which is, well, it's eventually related to permutations, but here's the problem. Here's the question. So let's look at a chessboard. So let's say 8x8 chessboard, and what we want to do. So maybe this is not quite 8x8, but etc. So imagine it's an 8x8 chessboard. Okay, and what I want to do is to place rooks, or what do we call rooks usually? Elephants in chess. So rooks are the pieces which can move either vertically or horizontally, right? So a rook on a chessboard is sort of the thing which you put at the end where you start. Okay, so all this is not required. You don't need no chess to solve this problem. So what I mean is, a rook on a chessboard, a rook in chess is a piece which has the following two allowed motions. It can either move vertically in its row or horizontally in its, vertically in its column or horizontally in its row. And the question is the following. You want to place 8 rooks on the chessboard. So I want 8 rooks on the usual, on an 8x8 chessboard. So I want to know how many different ways there are of placing 8 rooks such that none of them can attack any of the others. So 8 non-attacking rooks.
One way.
Okay. Sorry, what?
One way.
Is the question clear? So non-attacking rook meaning if I put two rooks in the same column, then of course they can attack each other, right? So I'm asking basically how many different ways are
So we
there
can put in the diagonal.
Diagonals, two diagonals.
Correct, but I mean there are many more possibilities than that. Just purely in terms of this this grid, it's like saying, can I choose 8 squares on this grid such that no two are in the same row or column? So it's not just diagonals. I could do many other things, right? So I could put this here, this here, this here, and so on. So as long as I ensure I don't choose 2 in the same row or 2 in the same column, then I'm okay.
So this will look like the permutation matrix, so 8 cross 8 permutation.
Okay, wonderful. This looks like an 8 cross 8 permutation matrix. Excellent. Okay, correct. So my question is, how many configurations are there?
So 8 factorial.
It's 8 factorial. Okay, so one way of seeing that this is 8 factorial is, well, because there are, well, it looks like a permutation matrix. That's a very quick answer. There are 8 factorial permutation matrices, but I mean, a permutation matrix is really, it encodes the permutation.
Is it 8 factorials?
It's 8 factorial, yes. It's the number of permutations of 8. Okay, why is that? I mean, just from, so recall there are 8 rows here. So how do you get a permutation out of a rook placement? Well, you look at the first row, the rook in the first row must be placed in some row, I mean, in some column, right? Because there are 8 of them totally. So there must be 1 in every row and 1 in every column. So you look at the first row, the rook in the first row must occur in some column. So let me say it occurs in, say, some column J1. So maybe that's where the rook is, in column J1. Then in the second row, the rook is in some column J2 and so on. So the rook occur as follows. You note down the row in which they occur, the column in which they occur. So row 1, column J1, row 2, column J2, and so on. And row 8, column J8. And if you sort of look at these numbers in the bottom, J1, J2, J3 till J8, well, what are they? They just form a permutation of the numbers 1 through 8, right? Because all the 8 columns must appear, so all 8 must be there, but they occur not necessarily in order, they occur in some permutation. So any non-attacking rook placement is in bijection with the set of all permutations of the numbers 1 through 8. Okay, so the number is in fact 8 factorial. So let's just do a couple of other similar questions. What if I had not an 8 cross 8, not a square chessboard, but say a rectangular chessboard? So suppose I had an M cross N chessboard. Let's say M is smaller than N. Okay, so I have M is smaller than N, and I only want to place R rooks in a non-attacking position. R is another number smaller than the smaller of these two. So I want, is the question clear again? I have a rectangular chessboard. So M rows and columns. So I'm asking how many ways are there of picking R cells, R boxes, such that no 2 boxes are in the same row or same column. So R non-attacking rooks, the number of ways of doing it. So how do we approach this?
So R into N.
Why R?
R into M choose M. First we have to fix one. R into N choose M.
No, R is the total number of rooks that I want to place, right? Okay.
So we have to fix one root in any M rows. Therefore we can choose N choose M. Possibility is for one root.
No, why is it N choose M? You mean N choose?
Either we can put in the column or row.
Yeah, that's okay. But why n choose m? So you're saying n choose m, right?
Yeah. Whether you can choose in the first box, that is 1 cross 1 or 1 2 position or 1 3 position or 2 1 position. First you have to fix first root. Maybe call as 1. There are R roots. Maybe we call 1 2 3 up to R.
Yes, okay.
We can fix 1 at anywhere.
The very first rook you can place anywhere. Okay.
Okay, that is m into n possibilities.
I see. You want to work like that. Okay. See, the point is that the rooks are all identical. Right? They're just identical piece. I'm not labeling. See, I cannot distinguish between the rooks. They don't come with. It's not like one blue color rook and a yellow color rook and a orange color rook and so on. So what you're saying is it would be a good idea if the rooks were all different. They all had 8, are different colors, so that placing the first rook, the blue color rook coming in some place and the yellow in a different place is a different configuration from what I would get if I interchange their positions. But what you're saying has again the same following problem that see, the first rook I can place here, and then you're seeing how many choices there are for the second rook, right? So maybe the second rook has many choices. Among them, one of the choices is I can place it here. But then you will be double counting the configuration as follows. You could have placed the first rook in this place. Instead of 2, I could have placed 1 there in its place. Right? This could have been my initial choice, and I could have placed 2 in the place of 1. Okay, so the very same configuration will be counted many times under this scheme. Okay. So because the roots are all identical, we will have to be slightly proceed in a slightly different fashion. So let's just do it the way we did for the square, for the case of the square chessboard. That, see, what do we know? The R non-attacking rooks must all occur in different rows and different columns for sure. Right? That much we know. So let's do the following. Let's choose. Choose the right thing to do here. Let's do the following. Let's choose. I could do it in one of two ways. So let me choose out of these m rows. I will choose R of these rows. Okay, so there are totally m rows. Out of these m, I will choose some R of them. Okay, some specific R of them I will mark. Okay, these are the R rows that I have chosen. And so why do I want to do that? Because those are the rows in which I'm going to place my rooks. So let's say, suppose here's a picture for R equals 3. I'm going to place 3 rooks in this board. The way I do it is I first choose 3 rows. Okay, so the number of ways of choosing. So again, we'll come to this in more detail next time, but I'm sure all of you have seen these MCR and so on. So there's a number of ways of choosing R objects from M objects. Okay, so I've chosen R rows. Now, having chosen these R rows, now how can I place the rooks? That's my question now. So I first chosen R rooks. Okay, so this multiplied by how many choices do I have now?
N choices.
N choices. Well, N choices for the first
R rows.
So these R rows. Let me call these label these rows as something. This is row 1 R. Sorry, I1, I2, IR. Okay, there are these R rows. Now in I1, the row I1, the rook can occur in any one of the n columns, right? So the rook in row I1 has n possibilities. So this is the rook in row I1. Okay, now what about the rook in row I2? In this row.
Except that one column.
Except the one column that you have already chosen for
n minus 1.
N minus 1. Now the next rook,
n minus 2 up to n minus r.
N minus 2. Okay, all the way till n minus r plus 1. So there are r total rooks. Okay, so this is the number. It's m choose r multiplied by n into n minus 1 into n minus r plus 1. Okay, and well, let me make this in a slightly more symmetrical form. Let me divide and multiply this number by r factorial. Okay, now why did I do that? What does the second term become? For those who have seen the formula of n choose r and so on. So this term here,
n minus r.
This number here is actually some
NCR.
It's just NCR.
NC.
Yes.
It's actually NCR because the usual way of writing NCR is n factorial by r factorial n minus r factorial. But that n minus r factorial I have cancelled on numerator and denominator. So that's exactly this number. So this box term is exactly NCR. So you see, you get this rather nice formula. It's NCR into NCR into r factorial. It's a very symmetrical thing. And of course, you should expect a symmetrical answer because instead of starting by choosing r rows, I could have started by choosing r columns where my roots are going to be placed, right? And then if I had done the analysis, I would have gotten, I should get the same answer. So there should be some symmetry between m and n here. And this shows that symmetry. Okay, so my time's up. I think I'll let me stop here for today, and we'll sort of pick up the thread from here in the next lecture. Thank you.
Thank you, sir. So, participants, the next two tutorial session will be on 29/11/20. That is next Sunday, from 1 p.m. to 2 p.m. first tutorial, and 5 p.m. to 6 p.m. second tutorial. So I request you all to join the session 5 or 10 minutes before the scheduled time. Thank you.
Okay.
Thank you, sir.
Yeah.
Thank you, sir.
Sure. I can stop my sharing, right?
Okay, sir.
I can leave. Yeah. Thank you.
Thank you.
Okay, sir. Thank you, sir. Thank you very much, sir.
Thank you. Yeah.
Thank you, sir.